Welcome to the lecture series of network theory. This is our sixth class on RLC network, where today we will learn about the basic concepts of parallel RLC network, and we will also solve a few numericals based on that concept. So let's get started. Now, as we can see here, we have a parallel RLC circuit where this resistor, inductor and capacitor are connected in parallel with each other, and this parallel circuit is energized by an AC sinusoidal voltage small v, where small v signifies the instantaneous value of that applied voltage. Now, since this is sinusoidal AC voltage, so the instantaneous voltage applied across that parallel RLC circuit is represented by V suffix m sin omega t, where we know that Vm represents the maximum or peak value of that applied voltage, and omega is the angular frequency of the supply, where omega is equal to 2 pi small f, where small f signifies the linear frequency of that supply. Omega, the angular frequency, is represented in radian per second, and small f, the linear frequency, is represented in cycles per second or hertz. Now next let's assume that this applied voltage supplies a current I. The small I signifies the instantaneous total current that flows or that is supplied by this voltage source. Now this I, the total current, will be divided into three parts and will be flowing separately through those branches, where IR, IL and IC represents the instantaneous current flowing through resistor, inductor and capacitor respectively. Now let's find the values of these currents one by one. So first we will obtain the expression of the current which flows through resistor. Now this instantaneous current can be represented by I suffix R, and we know since this is a resistor, it will obey simply the Ohm's law, and that will be V by R. Now V, this is expressed as Vm sin omega t, so it will be Vm sin omega t divided by R simply. Now next we will obtain the instantaneous current flown through the inductor. Now that we have already seen and learned in our previous classes that IL can be obtained by this expression for inductor, and that is 1 divided by L, where L is the inductance of that inductor, integration of V dt, where V is the voltage drop across that inductor. Here is it is the supply voltage. So if we now follow the rule of integration, we will be finally getting this value. So first we will put the value of this instantaneous voltage, that expression. So it is Vm sin omega t, and then we will integrate with respect to t. Now it will be minus Vm by omega L. This omega will come from this angle that we have for sinusoidal signal, and sine will become minus cos as we are integrating. So finally, by following the rule of integration, we will be getting this value for the instantaneous current flown through the inductor. Now since in our reference that we have taken, and that is voltage, we have expressed as sinusoidal signal or sinusoidal wave, so the currents that we will be here calculating, that will be finally expressed in terms of sinusoidal signal. So this cos will be, by following the rule of trigonometry, it will be expressed in terms of sine. So it will be cos omega t can be represented or can be written as sine 90 degree minus omega t, and this minus sign was already there in that expression. Now if we follow the rule of trigonometry, so we know that sine of minus theta is equal to minus sine theta. We are already familiar with this. So this minus sign can be taken inside, so this angle will be changed to omega t minus 90 degree. So this is the final expression of the current that flows through inductor, and here we have this omega t angle positive. Now next we will calculate the instantaneous current flown through the capacitor. Now that can be expressed as written as I suffix C, and already we know that is related to the capacitance of that capacitor like C, and also the voltage that dropped across this capacitor like C multiplied by dV by dt. So this is the first derivative of the voltage drop, that voltage that is dropped across the plates of the capacitor, across the capacitor. Now C, and in place of V again, if this small v, the instantaneous value, is replaced by this expression, so it will be Vm sin omega t, and if we follow the rule of differentiation, then finally we will be getting this expression omega c Vm cos omega t. Now again, this cos omega t will be expressed in terms of sine, so it will be sine 90 degree plus omega t. Here we will not use 90 degree minus omega t, as we have to finally express this omega t as positive, so here will follow 90 degree plus omega t. Now next we will add or we will take the algebraic sum of this individual currents, and we will get the expression of instantaneous current or total current that flows through that RLC, parallel RLC circuit, or that is supplied by that AC voltage source. Now that I will be equal to IR plus IL plus IC, and that is Vm sin omega t divided by R, the expression of the resistive current, plus Vm divided by omega L sin omega t minus 90 degree, that is the expression of inductive current, plus omega C Vm sin 90 degree plus omega t, and that is the expression of capacitive current. Now what we will do next is we will expand this compound angle of the sine term of both the sine terms. So following the rule of trigonometry, it can be written like this: first term will remain same, and for this it is sine A minus B, so it will be sine A cos B minus cos A sine B. So it will be V suffix m divided by omega L sin omega t cos 90 degree minus Vm divided by omega L, the same constant, then cos omega t sin 90 degree, and following the same rule again we will expand this compound angle, and we will be getting these two terms. Now we know that cos omega t we have already seen in our previous classes, the cos 90 degree is 0, so both of these terms will vanish in the expression of the total current, and sine 90 degree has value 1, so for these two terms this sine 90 degree will vanish, leaving 1 in those terms. So finally we will simplify that expression, and on the left side, as we can see here, this instantaneous value of the current has been expressed as Im sin omega t plus minus theta. Now this thing we have already seen in case of series RLC circuit, because I here this is the instantaneous value, so it will be expressed like Im then sine, and omega t y plus minus theta, because the voltage has been taken as reference, and since this is an AC circuit having both the AC components, inductor and capacitor, so definitely there will be a phase difference between applied voltage and current that flows. So if the net effect of that circuit, parallel RLC circuit, is inductive, then we will have some phase difference, and if the net effect of that circuit is capacitive, then we will have the same phase difference, but the sign will be opposite, and I will discuss that little later. So here the phase angle will be either positive or negative, and theta here express is phase difference between the voltage, the total voltage or applied voltage, and the total current. Now next we will simplify this equation, and we will be getting on the left side we already have Im sin omega t plus minus theta, and on the right side the first term will remain same, and this term will be expressed as minus Vm by omega L cos omega t, because sin 90 degree will be 1, and then we have the third term which is omega c Vm cos omega t, and sin 90 degree is 1. So in that equation on the right side we will have three terms. Now what we will do next is we will expand the left side, where again we have a compound angle sin a plus b or a minus b, that format we have. So we will expand this, so it will be written like Im sin omega t cos theta, and then plus minus Im cos omega t sin theta, and on the right side we are leaving the same terms. Now next what we will do is we will equate the coefficients of the like terms. Now here we have one sin omega t on the left side of that equation, and here we have one sin omega t term on the right side of the equation, and we have one cos omega t term on the left side, and we have two cos omega t terms on the right side of that equation. So next we will just equate this term and this term. So it can be written as Im sin omega t cos theta, and that will be equal to Vm sin omega t divided by R. And for rest of the part, it can be written like plus minus Im cos omega t sin theta from the left side, and from the right side it is minus Vm divided by omega L cos omega t plus omega c Vm cos omega t. Now next we will equate the coefficients of the like term. So from the first equation, the like term is sin omega t. So the coefficients will be, if when we will equate the coefficients, we will be getting this relationship where it is Im cos omega t will be equal to Vm divided by R. And then from the second equation, when the cos omega t is the like term, so when we will equate the coefficients, it will be plus minus Im sin omega t, and that will be equal to minus Vm divided by omega L plus omega C Vm. Now next our objective or our task is to get the phase angle or phase difference between the applied voltage and the total current, and that phase angle is here expressed as theta. Now the theta finally can be written as plus minus tan inverse and this thing, and that we can get this way. If we take the ratio of these two equations, then on the left side it can be written as plus minus sin theta divided by, and definitely we have Im, and in the denominator we have Im cos theta. So it can be finally written like this. We are just taking the ratio of both the sides of both the equations. So Im is the common term on the left side, so it will be, they will cancel each other, and similarly Vm is the common term, and definitely that has non-zero value. Now on the left side we have tan theta, and on the right side we have omega c minus 1 by omega L divided by R, this term. So if we calculate the only the value of theta, the phase difference, it will be tan inverse of this value, where we know that the capacitive reactance is 1 by omega c. So only omega c, it represents the capacitive susceptance, and omega L is the inductive reactance. So 1 by omega L is the inductive susceptance. So this is the difference of both the susceptances of these AC components. Now since this is a parallel circuit, so here we will be dealing with admittance and susceptance values instead of impedance and their reactances that we use in case of series circuit. Now if we simplify further, then it can be written as theta will be equal to this plus minus sign will be there on the right side, then tan inverse, and this it will be like in the numerator omega square CL minus 1, and this omega L will come in the denominator of this factor, and 1 by R. So R will go up, it will go to the numerator of this expression, so it will be finally R multiplied by omega square CL minus 1, and in the denominator we will have omega L. So this is the final expression of the phase angle between this applied voltage and total current. Now next we will find the maximum value of the total current through that parallel RLC branch. Now to get that maximum value, what we will do is we will take the square values of both the equations and then we will add them. So from the left side it will be Im square cos square theta, and from the second equation of left side of the second equation we will be having Im square sin square theta, and when we add them, then Im square is the common term, and inside bracket we will have cos square theta plus sin square theta, which gives us 1. So finally it will be on the left side, it will be Im square, and from the right side we will be having Vm divided by R, and that square value of that, and this value of from the second equation will give us omega c Vm minus Vm by omega L, and then square value of that. So simply that will be also added on the right side, and then directly this Im value has been written. That means it will be the square root of the whole term, means the square root of the addition of those individual square values. So this thing also we have seen earlier. Now Im has the value, only the value is this, and we know that I is equal to V multiplied by the admittance of that AC circuit, since here we are finding out the current, and if it was voltage, then we would have done or would have written like V, the voltage drop will be equal to current value multiplied by the impedance. Here has as a Vm, this value is common in both the terms, so Vm square, that will be taken common, and when it will come out of the square root, finally it will be Vm only. So Vm, and then inside that square root whatever we have, so Vm then multiplied by the admittance. So definitely this value will be the value of the admittance of that parallel circuit. So finally it will be written as Im, and that will be equal to Vm and then admittance of that parallel branch. So definitely the admittance value of that parallel RLC circuit will be this thing. So that has been shown here. Now we know that admittance of any AC circuit is expressed as G plus JB, where we know that G is the conductance of that AC circuit that comes from the resistance. So separately if we think, then G is the reciprocal of the resistance that we have in that RLC circuit. So G will be written as 1 by R, and then JB, here B is the net susceptance of that AC circuit. So if it is only inductive, then that will be the inductive susceptance. If it is capacitive circuit, then it will be only capacitive circuit, then it will be the capacitive susceptance of that capacitor. Otherwise, if we have both the AC components, inductor and capacitor, then it will be the net susceptance value of that RLC branch, or of that inductor and capacitor. So here, since as I have already said that this susceptance of that capacitive the capacitor will be J omega C, and for the inductor the susceptance value will be 1 by J omega L, and we know that 1 by J is minus J. So finally the admittance of that parallel RLC branch can be expressed like this. Now if we want to, this is the representation of rectangular format. So now if we want to represent this value, the value of the admittance in polar format, then that can be done by using the formula that we know. So here it will be simply the square of that real term and the square of the imaginary term. So here both the terms, these two terms are basically the imaginary terms. So J will be taken common, so inside bracket it will be omega C minus 1 by omega L. So when we will take the square value of that imaginary part, so it will be simply like this, and this thing we have already seen in the previous line when we have calculated, or when we calculated the maximum value of the current, and then finally we expressed as multiplication of the maximum voltage multiplied by the admittance. So this is the value of the admittance. Now here we are representing the admittance in terms of polar format, in polar format. So here along with the value, along with the R, because the polar format is R angle theta, so along with the R value, which is this, we have to also express the angle. Here angle means this, the phase difference between voltage and current. So here that we have also calculated, and that is tan inverse of this value, or this value. It will be plus minus tan inverse omega C minus 1 by omega L divided by 1 by R. Now next we will see when we will use this plus sign and when we will use the minus sign. Now this is the expression that we have seen in the previous slide, so just it has been repeated. So in here we have seen just Im, that is equal to Vm multiplied by the admittance, and then the admittance value has been calculated separately, and finally it has been represented in polar form. So just in this expression, this Y value has been replaced to express the maximum value of the total current. So Vm, and then this is nothing but the admittance value in polar form that we have expressed or obtained in the previous slide. Now we will see the phasor diagram of that parallel RLC circuit. So as we took the voltage as reference, so this is the phasor of applied voltage, and next we will draw the phasor of the current flown through the resistor. And resistor, we know that the phase difference is 0 between the voltage and current, so let's represent this as the phasor of IR, and then we will draw the phasor of the current that flows through inductor and capacitor. In case of pure inductor, the current lags the applied voltage by 90 degree. So let's take this as the phasor of the current that flows through inductor, and let's take this as the phasor of the current that flows through inductor. So this is, sorry, capacitor. Now next we have to take the net current for those AC components. So this much is IC. As we can see, IC has a higher value than IL. So this much IL we will subtract from IC, and that subtraction in the phasor diagram will be done from the end. So from here, if we take the value of IC, if we measure, and if we subtract that from IL, then this much will be the representation of the net current of those AC components. So it will be IC minus IL. And now next, if we draw the parallelogram between that IR and also that IC minus IL, then the resultant of that parallelogram will be the measurement of total current. So this will be the phasor of total current. So this is the phasor of total current, and this is the phase difference between the total current and applied voltage. So since here IC is more than IL, so we can say that the capacitive reactance is less than the inductive reactance, or capacitive susceptance is more than inductive susceptance. That means we can say that omega C is more than 1 by omega L. Capacitive susceptance is more than inductive susceptance, and that's why IC is more than IL. So if omega C is more than 1 by omega L, and if we take that difference, this will have a positive value, and 1 by R also is positive. So finally the value of the angle will be positive. And since the value of the capacitive current is more, that means we can say the net effect of that RLC circuit is capacitive. And we know that in case of capacitive circuit, current leads voltage, but if it is not only or pure capacitive circuit, then the difference between voltage and current will not be 90 degree, rather less than 90 degree. Now next, if we draw the phasor diagram where the inductive current is more than the capacitive current, so again V, the applied voltage, since this is the common factor, so we are taking that as a reference. And next we will draw the phasor of all the currents that we did for the previous case. So first we will draw the phasor of the resistive current, or the current that flows through the resistance, and let's that take as IR. And now we will draw the phasor of the current that flows through the capacitor, and that we again represent as IC. And this time the value of the current that flows through the inductor, that is more than IC, so it will in the phasor diagram also it will have more value than IC. Though the phasor diagram is not to scale, but at least we can understand this IL is more than IC. Now to get the net current value, what we will do again, this much value of IC we will subtract from IL, and that we will do from this end. So let's say this much is the IC. So from IL we will subtract this, and then this much will be the difference of the inductive current and capacitive current. So next what we will do is we will complete this parallelogram, and we will draw the resultant. So that will be the phasor of net current of this parallel RLC circuit when we have more or dominating inductive nature. So this is the phasor of the total current I, and this angle is the phase difference between the applied voltage V and the total current I. Now here, as we can see, the total current is lagging the applied voltage, and here what we assumed was the inductive effect is dominating. So that means the susceptance of that inductive circuit is more, or the reactance of that inductive path or inductive reactance is less. That's why the current through that inductor is more. So susceptance of inductive path will be more than the susceptance of that capacitive path. So when we will take the difference of these two, and in the expression of that phase angle, this will give us a negative value. So that means the phase angle will be negative, so it will be minus tan inverse, and this is, since this is negative, this will give a negative value. So finally that negative term will come out, and it will be, then we will take the only the value, and then divided by 1 by r. So that will give us a negative phase angle, and we in the phasor diagram also that we can see that the I is lagging the applied voltage. Now finally we will represent the instantaneous current that flows through the parallel RLC branch. So that instantaneous current can be expressed as small I will be equal to Im, the peak or maximum value of the total current, and sine omega t plus minus theta. And this value of Im, we have already seen that that value is Vm multiplied by the admittance value, and this is the admittance value that we know. Then sine omega t plus minus theta. Here the in the expression of the admittance we had the phase angles, but here since we are incorporating that or considering that phase angle inside that sine, so that's why here we are not separately writing the phase angle, rather this phase angle we are writing as the phase value of the sinusoidal signal. So finally it will be sine omega t plus minus, and then in place of theta we are writing the value of the theta that we have seen earlier, and that is tan inverse, or here plus minus, so we have to also consider this plus minus sign, here plus minus tan inverse, and this value. So this is the explanation of the expression of current or the value of the current that we get in case of parallel RLC circuit, and also the phase difference between the applied voltage and the current that flows, and also if it is has the net effect of the circuit is inductive, then what happens, or what is the phasor diagram, or what is the phase angle value, and if the net effect is capacitive, then what will be the phasor diagram, or what will be the phase angle value that we have seen so far. Next we will solve a numerical based on parallel RLC circuit. Now again we have this parallel RLC circuit where it is written that 200 volt 50 hertz AC voltage is applied across a parallel RLC circuit. So that means the value of this voltage, this is 200 volt, will be the RMS value of that applied voltage. Otherwise, if it was given in the form of expression of sinusoidal signal, then that would have been taken as the instantaneous value of the applied voltage. This is RMS value of the applied voltage, and that is 200 volt. And the frequency of the supply, the linear frequency, is 50 hertz. These are the two information that we are getting from the first part of the problem, and then the values of that RLC circuit. So R is given as 10 ohm, L is given as 20 millihenry, that means 20 into 10 to the power minus 3 henry, and the C, the capacitance of the capacitor, is given as 500 microfarad, so 500 10 to the power minus 6 farad. And what we have to find is the RMS and instantaneous value of the total current in that circuit. So here first let's assume that this instantaneous of this AC voltage, AC sinusoidal voltage, is supplying this AC current I, and through every branch these are the currents that are flowing separately. So IR, IL and IC, and definitely I will be the summation of all these individual currents that we have seen already. Now we will find the instantaneous value of those individual currents. So first IR, and that will be the voltage, simply voltage divided by the resistance value, and that is 10. So it will be 20 ampere. and this value is the RMS value. So RMS value of the current that flows through the resistor. Now next we will find the current value that flows through inductor, and this time again we will find the RMS value based on the RMS voltage that is given for this circuit. So IL will be simply the voltage, RMS voltage, divided by the inductive reactance or reactance of that inductor or inductive path, and simply that is X of L. Now separately we will find the value of XL, and definitely for IC we will need the value of XC, so we will find that value. So XL, the inductive reactance, we know that is omega L, or we can say J omega L. In rectangular format it is J omega L. So this is a rectangular format, and in polar format if we represent, then it will be omega L, and then angle will be 90 degree, we know, for the J part. And since we don't have any real part, so that's why the angle will be 90 degree, since it is plus J. Otherwise if it was minus J, then the angle would have been minus 90 degree. So XL will be again 2 pi f, and then multiplied by L. 2 pi and f value is 50. So 2 into 50 into 3.14 will give us 314, and then the inductance value, which is 20 multiplied by 10 to the power minus 3, and then angle is 90 degrees. So finally it will be, this will give us 6280, 28 and 6, so 6280 into 10 to the power minus 3, and the angle is 90 degree, and since this is reactance, so unit will be ohm. Or we can say, if we simplify further, then 10 to the minus 3, so it will be 6.28, and then angle is 90 degree, and this much ohm. Now next, if we find the value of Xc, capacitive reactance, then we know that is 1 by J omega C, or we can say minus J 1 by omega C. So because of this minus J, it will be if we represent in polar format, then it will be value wise, it will be 1 by omega C, as the real part is missing, so it will be square root of the square value of this, that means this value only. And because of this minus J, the angle will be minus 90 degree. Now if we put the values of omega, that is already 314 we have seen, and that is the same value, and capacitance value is this. If we put this to value, then 1 by omega C will come as 6.37, and then the angle is minus 90 degrees. So in the polar form, the value of capacitive reactance will be this much ohm. Now in place of XL in the expression of current, we will put the value of this XL, what is 6.28, and then angle wise it is 90 degree, and since this was reference, the voltage, and the angle was not given, so for the reference quantity it will be, the angle will be 0 degree, we know that. So now if this is we are dividing two values which are given in polar format, so simply it will be 200 divided by 6.28, and that will be 31.85, and angle wise, the angle that we have in the denominator will be subtracted from the angle that we have in the numerator, and that will be 0 minus 90 degree, so it will be minus 90 degree. This is current, so unit will be ampere. Now next we will calculate the value of the current that flows through the capacitor, and this time it will be 200 divided by Xc, the capacitive reactance. Capacitive reactance is 6.37, so it will be 200 divided by 6.37, and angle wise it is minus 90 degree. Again this angle for the reference quantity, it will be the angle, phase angle will be taken as 0 degree. Now 200 divided by 6.37, it will be simply 31.40, and it will be 0 minus of minus 90 degrees, so it will be plus 90 degree, and this much ampere. Now next is to get the value of the total current, and this was RMS values, so the value of the total current also will be RMS value, and this will be simply the IR, which is 20, and then IL, which is 31.85, then minus 90 degree plus IC, which is 31.4. This is not degree, this is only the value, and 90 degree, then this much ampere. So since we are adding three values, so it will be better if we express them in a rectangular format. So to represent in rectangulars, the first value is already has the real value in resistive current, so it will remain the same. So it will be 20, now 31.85, and it can be written as cos of theta plus j sine of theta. So cos of minus 90 degree, that means cos of 90 degree. Cos of minus theta is equal to cos theta, so cos of 90 degree, and then plus j sine of minus 90 degree. So sine of minus theta is minus sine theta, so it will be finally minus j then sine 90 degree, and then this term it will be 31.40, and then if we take the rectangular form, then it will be sine 90 plus j cos 90 plus j sine 90 degree. Now we know that cos 90 is 0, so this factor will vanish, and sine 90 will give us 1. So it will be 20 and then minus j 31.85 as sine 90 contributed 1 only, and then plus j 31.40. So finally it will be 20, and 20 is the only real value, and these two imaginary values will be simplified. So it will be 20, and then finally it will be minus j, it will be 0.45, this much ampere. So either we can express this in rectangular form, but since we have to also know what is the value of the phase difference, so it will be represented in polar format. So if we represent this in polar format, again we can use the formula, or we can use the calculator or anything. Now it will be finally r angle theta in that format. So r will come as almost 20 because this is 0.45, so it will be around 20 only, and the angle wise it will be minus very small value, minus 1.3, because as we have seen here, the current that flows through inductor is 31.85 and through capacitor is 31.40, almost same. That means in the circuit their effect is almost same, but since this current has more value, the inductive current, so net effect in the circuit will be inductive, and in case of inductive circuit the current lags the applied voltage, so definitely the phase angle will be negative finally, and that's what we have achieved here, is we have obtained here, that is minus 1.3 degree, but it has very small value, and this much ampere, this is the total current or RMS value of the total current. Now next we will represent the expression of the instantaneous current, and that is, we know it, that is Im sine and then omega t plus minus theta. In this case we have seen that the net effect of the circuit is inductive, and for that the phase angle has come as negative, so that's what we have written here. Now Im, we know it is the RMS value multiplied by root 2. So RMS value we obtained as 20 and then 1 root 2 or 1.414, this much, and then sine and omega t, and the phase angle itself is negative. I mean, that's negative sign we have already considered here, so it will be only the value 1.3 degree. 1.3 degree ampere, and 20 multiplied by 2 will give 28.28, and then sine omega t minus 1.3 degree. So this much ampere, and initially in the problem statement the value of the voltage was given as 200 volt. So if we are interested to express the voltage, instantaneous value of that voltage, if we want to express that, then that will be our Vm. So it will be RMS value of the voltage multiplied by root 2. So it will be RMS value was given as 200, then root 2, and since that was taken as the reference parameter, so it will be simply omega t. There the phase angle after omega t will be 0. So 200 multiplied by 2, that will give us 282.8084, and then sine omega t, and this much volt, since this is the expression of voltage, so this much volt. Now how will be the phasor diagram of this parallel RLC circuit that we have already seen? So I am not redrawing that circuit. This will have this nature where IL has more value than IC. So finally the phasor diagram of that circuit will have this nature. So theta will be less than this value, but theta will be negative. So this was the all about the basics of parallel RLC circuit. In my next class, I will discuss about a few more numericals based on RLC circuit. So with this, I end today's class. Thank you.